Hi, folks. My name is Alex Garnett. I am a developer advocate at Temporal, and I am excited to talk to you today about building reliable distributed systems. You're going to see some examples of error handling and workflow management. Let's get started. Today, we're going to review what modern applications look like and why Temporal is beneficial to them. We're going to talk about durable execution as a concept. We'll review an example temporal application, see it in action, and then see what recovering from failure looks like. So, modern applications are generally distributed systems. What this means, they may have their functionality split across multiple microservices, accessed via a network, and you're probably running multiple instances of a single service for failover and replication. What kinds of things go wrong in these distributed systems? Well, external APIs might go down, your database could go offline or fail over temporarily, queues could back up, and things could time out. A lot of modern applications just wind up being queues on top of queues on top of queues for this reason, and that's often an architecture bottleneck. Also, sharing state is challenging. If you need to have some kind of RPC implementation for one part of your stack to talk to another, you don't always want that to be homegrown. You have to guarantee idempotent transactions, meaning that if you try to write the same database two or three times by accident, you don't want that to cause duplicated data. And you have to somehow manage long running processes in a way that is observable and scalable. The more powerful your systems get, the less intuitive they are for developers to work on, right? You can't just sit down and kind of code some HTML from scratch or something fun like that. There's all kinds of abstraction layers. You have to learn Kubernetes, all this stuff, right? And so you wind up with decreased feature velocity. Your systems become more challenging to work on, and it's hard to get end to end visibility into what they're doing. But we're very happy to say we have the tools to help you with this. Temporal helps you add features like compensating transactions, load balancing, batch processing, and this is not the kind of thing that you want to have to reinvent from scratch at every single project, every single job that you take on. So, pleased to say there is an easier way, and that's a concept that we call durable execution. Durable execution is crash proof execution. It's a development abstraction that automatically maintains application state and recovers from failure. It ensures your applications continue execution despite any adverse conditions, and it improves developer productivity by making applications easier to develop, scale, and support. Well, what does crash proof actually mean in this context? Let's think about it. When we're talking about a normal application that's not benefiting from durable execution, it's not as if, your code's going to crash due to bugs in it. It might, but that's not really what we're talking about when we talk about crashes. If you think about a regular distributed application, many things can fail, can go down. You could lose the network, you could lose some part of your disk, might not be able to write. You'll have to bake in some kind of queue to handle that in the meantime. And as such, most applications are constantly writing to databases or persisting some flags elsewhere, or trying to communicate back up to some orchestrator so that when anything bad happens, you don't have data loss, you don't have downtime. And you spend a lot of your time building in support for all these edge cases to make your applications more durable. Not because of crashing just due to bugs on your end, but due to other uncontrollable circumstances. You've always got to do all this additional work to make sure that you're persisting data and you're persisting that application. With durable execution, you get all this for free. So, this is really the key concept. Temporal is an open source durable execution platform that reduces code complexity, makes your application more reliable, and helps you deliver more features faster. It abstracts away the complexities around retries, rollbacks, queues, state machines, and timers. You can write in your choice of programming language. We currently have SDKs for Python, Go, Java, TypeScript, PHP, .NET, Ruby, and more on the way. They're all very nice and idiomatic, and basically you're just rebasing onto a few of our core temporal primitives. You deploy and run your code in your environment, so you always have control over where you're actually executing your logic. And Temporal provides a fault-tolerant durability layer so you can recover from any failures. Temporal primitives have a few key concepts. There's workflows, activities, workers, task queues, and the temporal service, which we'll talk about briefly so you have an idea. Workflows are the core steps of your process. Any variable that's written to in a workflow, we automatically persist that state, and we can maintain that state and fail over even after a crash. Workflows can sleep and they can receive incoming messages, so you can easily integrate an external UI. You can run and keep running workflows for years, even surviving any infrastructure failures, and they are written in a language of your choice. Activities are the subunits of work within those workflows. So, activities are where you call remote services, process files, or send emails, anything that has to do some kind of atomic operation that belongs in an activity. Those are also written in a language of your choice. There's two major constraints between workflows and activities. Workflow code should be deterministic because we need to be able to replay it and fail it over to rebuild state when needed. Activities should be idempotent in case they fail and are rerun. Those are really the two key concepts of building with Temporal. And if you follow those two key concepts, you get all the benefits of durable execution and replay and recreating state as needed. Workflows help you build durable apps. Workflow code orchestrates the execution of activities and persists the results. If an activity fails, the workflow runs the activity again by default. You can configure this. You can add more conditional retry logic. If the application itself crashes, Temporal will automatically recreate its pre-failure state so it can continue right where it left off. It does this by embedding itself in different parts of your workflow code and persisting events server side every time your workflow progresses through a new state transition. Workers are what actually run your workflow and activity code. You run them on your own servers, you deploy them like any other application. That way, you are in charge of your execution environment. And the way workers work is they will pull task queues on the temporal service. As workers encounter workflows and activities that need to be done, those will all get executed by pulling that task queue. And you can deploy your workers into scalable Kubernetes pods. That way, you've got lots and lots of workers watching lots and lots of task queues, and you can get some fine grained control in that way. The temporal service is the heart of it all. That's what manages the execution of your workflows and activities. That's what actually handles all this state tracking on the server side, and that gets you lots of nice observability features as well as our web UI, which you'll see in a second. As your applications progress through those different state transitions and complete tasks, it will add events to the event history on the service, and all connections are outbound only. Temporal does not need access to your network. All right, now we're going to do some demos. I have here a Temporal dev server running on my machine. It's built into our command line client. I have the Temporal web UI displaying in a browser tab, which you'll see populate in a second. And I have some sample workflow code, in this case for working with an e-commerce system. So we're going to show some sample workflows for ordering sneakers and all the ways that Temporal can help with some edge cases that might come up while you are working on that. So first thing I'm going to do is kick off a workflow that's just going to run end to end, no problems. So we've got to dispatch the workflow and it returns automatically within just a couple of seconds. If I reload this browser tab, you can see we've got one workflow logged in this temporal service. And I can click through and show off a bit of what our web UI looks like. Here you can say the input that was passed to this workflow, as well as the result that came out, which was just a confirmation string talking about there were 2 items in the order and the order got delivered. If I scroll down here, you can see the entire workflow event history first displayed as a sort of a timeline view. Here's the whole workflow end to end, and here are the 3 activities that were run as part of that workflow. So you can see process payment, reserve inventory, and deliver order all were executed in a sequence successfully as part of that workflow. Down here, you can see all the state transitions that workflow went through as it was scheduling and completing those activities. So every one of these state transitions comes directly out of the Temporal SDK code that was used to write this workflow, and Temporal has the means to roll back or retry from any of these steps going wrong or needing to fail over onto a new worker due to any kind of unexpected downtime. Now we'll change this workflow in some ways so you can see some temporal features in action. The first thing I'm going to do is uncomment this function, and that will make it so that the inventory pretends to go down the first few times it tries to run through, and you'll see temporal performing some retries. So we'll pull this back up, and I will rerun the workflow. All right, I'll reload the web UI. Here you can see another workflow registered on the temporal service. I'll click through into this workflow, and you can see this reserve inventory activity is failing. Okay, it's first here on its first attempt, and it's going to keep trying. Now it's already on attempt number 3. We've made it so that it's automatically going to fail the first 4 times it tries to go through. And Temporal is making use of its retry functionality to automatically rerun this activity every time it doesn't quite complete successfully. And so Temporal is able to do that internally by itself. On the 5th try, it works successfully. And again, you can see all these activities run end to end successfully to complete the workflow. Okay, now back to the web UI homepage. We're going to make a couple more changes. We're going to comment this back out again so that it works the first try. And now we're going to change the credit card number that we're passing to the workflow as input so that it's an expired credit card expiration date. We have a check right here to see if the credit card is expired. We should fail the workflow. And in our workflow definition, we have this credit card expired exception listed as a non-retriable error type. This way, if you have bad data passed to your workflow and you know you don't want to get those retries out of the box, you can specify errors that will not be retried and will automatically be failed just to save time and not get the retries running where you don't actually want them because they would not benefit. Right here, I've gotten a TypeScript traceback pretty much immediately after kicking off that workflow with bad data because we deliberately have that marked as a non-retriable error. I can click through here. You'll see the traceback is stored as the workflow result, and we have the activity marked as failed, which, because we had it as a non-retriable error, failed the entire workflow. So you can see we definitely wanted to fail in this case. We had some bad data, and we knew we weren't going to be able to progress. We did not want to keep retrying there. All right. I will put that back, and I will also change our workflow definition slightly here. So first, let me make that 1226 again. Now what I've done is I've added a signal handler to our workflow right here. And what that's going to do is it's going to block and wait for manual approval of the input that we're providing before it progresses through those activity steps. We'll do this. We'll bump it up to 1,000 sneakers we're buying. That way, it's going to get caught by this check that says if an item quantity is over $10,000 in order, we want to stop and wait for input in the workflow. The reason we have signals is so that you can design any kind of human in the loop temporal workflow, whether it's a UI that's waiting for some kind of input or any application that has to receive some kind of signal from an external application. Workflows don't have to run end to end all at once. They can wait, they can block. A workflow can be a really long lived construct, and you can just put all of your data into a workflow and just persist that indefinitely because Temporal has that durable execution functionality. Workflows don't need to return in any amount of time. They can wait until some other step comes in. In this case, we're just waiting on this string called approve order. So what I'm going to do is you could have like a UI that sends this string along. In this case, I'm just going to pass it as a string here right In the Temporal web UI, signals can also have additional metadata or other input parameters, but in this case, we just are looking for a name. I'll send the approve order signal. You see it logged in the event history right away, and the other activities are then able to run and complete as expected. So there's some temporal feature demos. All right, that's it for me today. Thanks for paying attention. You can use this QR code to keep up with the temporal community.